Welcome and good afternoon. My name is Bethany Maddox, and I'm a member of the customer care team here at Vitech Corporation. I'm very pleased to be your host for this webinar today as we discuss Systems Engineering Lite. Before we get started, I'd like to take a few moments to review some technical details. First, questions. Please feel free to submit your questions at any time via the Q&A function in the GoToWebinar window. We will be monitoring these throughout today's event. We plan to respond to questions during a Q&A session at the end of the webinar. The webinar is being recorded today. If you have technical difficulties during the presentation, an online archive with this presentation will be available within 24 hours of the live version. I believe that takes care of all our housekeeping matters, so let's get started. I'd like to take a moment to introduce James Kolos, our speaker for today's presentation. James is Chief Engineer at Synchronous and has worked in product development for 15 years. He's managed numerous projects from small research and development efforts to large integrated product development efforts. Please join me in welcoming James Kolos.
All right, thank you, Bethany. This is Systems Engineering Lite. And first I'd like to start out with the intended audience for this talk. This talk is for technical project managers, new systems engineers, companies that may be considered small or medium-sized, or even large product development companies that are seeking to simplify their systems engineering processes and tools for their smaller projects. Senior systems engineers are welcome as well, and may be able to use this information to simplify some of their processes for their smaller projects as well. So a little bit of background. I work for Synchronous. We're founded in 1998 and located in Denver, Colorado. We assist companies with research, new product development, and sustaining engineering efforts. We've grown rapidly in the last few years. We now have about 70 engineers in all different disciplines, from mechanical to electrical to software, and of course we have project management and systems engineering on board. Now, over the years, we've developed mature product development and project management processes, but systems engineering was only introduced about 2 years ago through a strategic hire. We hired a vice president who had experience in the defense and medical industries and has done systems engineering for 20 years. And he introduced that to Synchronous, and then it was initially a struggle to figure out, well, how do we take this very large, complex discipline and roll it into a small company like ours? So how much systems engineering do we do at Synchronous? Well, we do have a variety of project sizes, and for our larger projects, we do have a detailed system engineering process and set of tools that go with it, and we actually do use model-based systems engineering tools, in this case Vitech Core, for our larger projects. But we do have lots of smaller projects, and we're struggling to figure out exactly what level of systems engineering was appropriate. And by small to medium, what I mean is anything from a month to a half a year in duration, and these projects often only have 2 to 4 people on them total. So other characteristics of smaller projects are they have few requirements, simpler deliverables. There may be fewer engineering disciplines involved, so there may be just a simple mechanical project or a project to design a new PCB. So it may only have one engineering discipline. Fewer staff and organizational structures. Trade-offs are typically less complex, or the architecture is simply dictated to you by the customer, and fewer and simpler interfaces. So we found that there were few resources available to us when we looked out into the system engineering world for help on how to tailor this discipline for a small business or a small project. And our difficulty is as we've grown and added all these other disciplines, even some small projects can have a significant amount of complexity. Especially with the proliferation of graphic user interfaces. You may have a project that's got industrial design, mechanical, firmware, software, all in one project. and it needs to be done in 4 months. And yes, people talk about tailoring systems engineering. In fact, the NCOSE handbook of 400 pages has a whole section devoted to it. It's about 8 pages long. It tells you to tailor it, but doesn't really tell you how. It doesn't tell you, hey, this is the minimum setup you need to do system engineering on a small project. Now, NCOSE is aware of this problem, and when I was at the conference last year, I learned about a very small and micro entities working group, and they are working very directly to address these issues, and I believe they're going to be releasing something in the next year or so. But until then, we're kind of on our own. And so initially what we tried to do was put both a project manager and a systems engineer on a small project. And what we found was they sort of didn't work super well together. They ended up doing each other's jobs quite a bit. And so when on this small project, it ended up being rather inefficient, believe it or not, because we had 2 full-time a system engineer and a project manager. And when we examined their workload and what they were doing at each phase, we found that they sort of offset each other. When the system engineer was busy at the beginning with requirements gathering and architecture, the project manager wasn't as busy. But then as we moved into development, project manager took over, and then later on in verification, the system engineer took over again. So what we're trying to do and what works in a larger project to have these independent disciplines actually works better to combine these 2 disciplines into a single person. We call them the PMSE, the project manager slash systems engineer. And this is what we do on these System Engineering Lite projects is we have a technical project manager and we add some systems engineering capabilities to them. So the goals of Systems Engineering Lite are to make these systems engineering tools available to a technical project manager on these smaller projects. It's a combined role, and we don't want to overburden them. We want to add just enough systems engineering to add value to the project. And by value, we mean better systems definition, better project quality, and improved communications, both within the project team and with the stakeholders. So to do this, we introduced a set of System Engineering Lite tools, and I'm going to go into each of these in more detail. But at the beginning of a project, we figure out, okay, given this particular project and what it's required to do, what kind of System Engineering Lite tools do we want to use? What makes the most sense? And at a minimum, all projects require a product requirements specification. And then as the projects get more and more complex, we add more of these tools to them. Now the important point here is, yes, we have a lot of different kinds of tools that we're using, but none of these actually require specialized systems engineering software tools. For these types of projects, we use typical Office software, including Word, Excel, PowerPoint, SharePoint, and Visio. So experienced systems engineers may be looking at the list and saying, well, what about this and what about that? Yes, there's a lot missing, but that is the point. We have to remember that we're trying to add some systems engineering capabilities to the project manager, not turning them into a full-blown systems engineer. It's an important distinction on these smaller projects. So throughout the rest of the talk, I'm going to be referring to this example project that we actually use System Engineering Lite on as one of our pilot projects. And this is for a project for TD Williamson. They make oil and gas pipeline tools. And this is their automated combo pigging system. And this system uses these spheres that you can see in the picture on the right to automatically clean a pipeline of water buildup. It helps lubricate and clean the pipeline as well. And so while they were developing this new system, they hired Synchronous to help out. They were a little low on resources and needed some help. And so our part of this overall system was 2 major subassemblies. One was the dual pin hydraulic subsystem you see on the right, and one was a control subsystem with a graphic user interface and also remote access capabilities that you see on the left. The customer was in charge of everything else that you see there. Some interesting parts about this project is that it's in an explosive gas environment. This is a gas pipeline, and there are gases in the air that can explode under the right circumstances. So all of our systems had to be hardened against that. We also have to be able to support the launch of a non-spherical pipeline tool. So at certain points, you can change the software to manual mode and then launch a different type of tool. We used a PLC for the control system, and that was actually novel in this environment. They had never done that before. And so that had some new challenges, a new way of doing things. And for reference, the older systems actually just used basic mechanical switches and an LED interface of lights lighting up, green and red. There was no graphic user interface and no real detailed feedback to the users. The older systems also didn't have any remote access, so that was a new challenge. They'd like to be able to run this thing remotely so that the people don't have to be out there every time they want to change it. And then this is also a concurrent design with the customer. So while they were designing the rest of the system, we were designing some major subsystems, these control pieces, and it required very, very clear communication to support the project pace. So there's a lot of back and forth, and we had to use something to really help with that clear communication. The project was in multiple phases. The first phase was about a month long and focused on gathering requirements and some trade studies on how to actually launch those tools with the pin styles, and then a trade study on the electrical control interface. And like I said, we settled on a PLC type control for that. Phase 2 was the actual development effort, and it was just under half a year. Fleshed out the rest of the architecture, and then designed and documented the system, and then procured and built 3 systems, and did some on-site integration as well. And phase 3 was mainly software support. As they fielded these systems, they got feedback, and we helped clean things up a bit. So now we're going to get into the various tools that we use on Systems Engineering Lite. And the first one is our product requirement specification. But before we can put that together, we have to gather requirements. And in an ideal world, the stakeholder, the customer, will give you originating requirements. And so they give you this document that's called a system specification or something like that. And then you go and put it into your system and evaluate the requirements and whatnot. More often, what we're given is an email or a conference call or some meeting, and maybe a regulatory spec or two that we're supposed to follow. And so what we end up doing often is having to pull the requirements out of the customer. And to do this, we use a questionnaire. More experienced people have these questions in their head. But we actually have to sit down with the customer and figure out often what they really want their system to do. And then from there, derive and manage the requirements during the early phases. So the PRS itself is a document. We often use SharePoint, a list in there. But each of the requirements has the following attributes. It has a unique identifier. It has a name. That's what we call the requirement. It has a detailed specification that's as quantified as possible. And I'm not going to get into how to write a proper requirement. There's been many books written on the subject, and you can do the homework for that. Some of the other attributes that we have for the PRS are status, which I'll get into in a second, the source. So where did this requirement come from? Did we make it up? Did the customer tell us? How did they tell us? Was it an email? Was it a meeting? Was it an actual document that they give us? And then the verification. How do we know that we actually succeeded in implementing this requirement? And I'll get into that in just a second as well. So what we've found is because customers may not be experienced in how to write requirements, these requirements are ill-defined. And so we end up writing the requirements ourselves. And so we use the status attribute to let us know just how well our PRS is doing. And so we can have 4 different statuses on a particular requirement. And starting at the bottom is an unknown requirement. Means we have something here that we need to do, but we don't know exactly what the requirement is yet. It's kind of a placeholder. And a good one for that is, hey, there's an environmental requirement. The customer hasn't thought through, well, does this have to be an IP-rated device? Is it going to be outside, inside? So unknown is, let's figure this out. An estimate is a requirement that typically Synchronous has tried to derive, but we haven't got quantitative values yet. Preferred is, we know what the requirement is, we've quantified it, but there's still some uncertainty or doubt about it, and the customer hasn't necessarily seen or approved it yet. And our goal is to get every requirement up to the firm level, which is a known requirement that's been quantified and customer approved. And so what we do is at every meeting with the customer, we bring up our PRS, and we have these color-coded, and so we look for anything that's not firm and try to firm it up. We also include the verification activities directly in the PRS. And this may or may not work for every project. If the project is small enough and the verifications are simple enough, you can put your results directly into your PRS. Often we'll put a note in the verification column that says, see this verification document, which would actually have a procedure and results for more complex verifications. But the point is you do need to verify every requirement. You have to know how you're going to test it and who's going to test it and who's going to pay for that testing. We've been burned many times in the past when you get through a project and you get to the end and customer sees how it works and that's not how they expected it to work. Well, nobody ever agreed on what the verification was at the beginning. That would have solved it. So common verifications are inspection, we look at it and agree as to what it's doing. Analysis, this could be CAD analysis or spreadsheets, actual testing or demonstrations. And like I said, we can put these verification results directly in the PRS. So next is the physical block diagram. And this is a great tool to give everybody a combination view of the system. Shows our rough layout and shows our basic interfaces and signals. It also helps define what's in and out of our system. It's amazing how often you draw one of these and customers say, well, what about X? And you forgot to put this in, and well, maybe we didn't forget, maybe you forgot to tell us. So this really starts the dialogue of what are we actually designing? And we can also use this for allocating functions, which I'll talk about later. So here's a picture, a schematic of that T.D. Williamson system. And what you see is a really rough representation of the physical parts. But they do have some relation to each other in space. Here's that stand that contains the electronics enclosure and the computer and the display and our button interfaces. That's mounted onto the skid that they provide. And then we have our hydraulic subassembly up here. And the very obvious bright red dotted line is what's inside of our system and what's not inside of our system. So we're not responsible for remote sensors, we're not responsible for the infrastructure or the hydraulic power unit or the remote computer. We are expecting to get or communicate with RS-232 signaling to that remote computer. We're expecting to get power in the form of 24 volts from somewhere. That's not our responsibility. And we have various signals coming in and out of our system. So now at a glance, everybody can get on the same page as to, hey, yeah, that is the high-level view of this system. Next is EFFBD, or an Enhanced Functional Flow Block Diagram. And with this, you want to meet with multiple stakeholders from the customer to really figure out what the behavior of the system is. And if people aren't used to thinking in terms of behavior, it's easy to get bogged down and go into architecture. So it's really critical that you focus on what is the logic of the system, what is the system supposed to do, not how does it do it. And the more people you can get involved that have a say in how the system works, the better. Because yes, the management may think they know how it works, but until you talk to the tech people and figure out what the problems are with repairing a system such as the one you're designing, you will miss a lot of requirements and functions that may be obvious to these guys, but not obvious to the managers. We also like to work in layers, so we call them functional black boxes. We start at the system level and say, okay, what does the system high level need to do? And then what do each of those sub-functions need to do? And we basically construct what I call a fancy block diagram. And because we use core, we have the similar constructs as what they use. So things and the functions in the blocks can either be sequenced together, they can be paralleled, selected, decisions could be made, things can iterate or loop. We also use information blocks to understand the flow of data or objects between each of the functions. So let's see what this looks like. Now at the top level, you'll have the system and any external functions above what you're seeing here. But now we dive into the system. What does the system have to do? What are the functions of the system? Well, first step is you have to install the system. So that's going to require a set of functions that go in there. And once it's installed, you're going to go into normal use activities. Occasionally, you'll have to service the system. And then you'll loop back to normal use and kind of do this for the operating life of the system. And then eventually you'll have to dispose of the system. And we actually use this template as a starting point for most of our projects, it turns out. But what differs at the next level down is what's under normal use. Well, the next level for this particular system is this. So normally what happens is you start in a locked status. So the PLC is locked and the display is actually sleeping. And until you push a button to wake up the display, it's saving some energy and blacked out. You push that button and you try to unlock it. You go to this unlock function. If you succeed, you continue. You succeed by putting in your PIN, as you can see here. If you fail, you go back to a locked status. When you succeed, now we go into another AND construct here. You go into your normal operating modes, which is another black box, and it has various inputs. And in the meantime, what's happening in the background is a lock timer is going, and it's monitoring your button presses. So after 60 minutes, if it hasn't detected a button press, well, it's going to lock, and you'll go back to the beginning here. So now we have another black box of operating modes. Let's look in there. And we actually have 4 operating modes that we can cycle through: manual, timed, alternate scenarios, and configuration. And I don't know if you noticed from the physical block diagram, but we only have 4 buttons that can affect this system, and we have a variety of sensor inputs that can affect the system. And so there's a bunch of functions that these buttons can control within the graphic user interface. There's different positions for our actuators and sensor signals. All of that is integrated into the functions that live under each of these, and the only output of all of these is the valve control. So all those things are integrated, decisions are made, and we take and control the output of 4 valves to make the system operate. So next is our physical architecture. So this is kind of the reverse of our EFFBDs. This is the physical world. The EFFBDs were the logical world, and now here's the physical world. And I view this basically as a high-level bill of materials. We see our system and our assemblies and sub-assemblies in a hierarchical context. We also use this to clearly assign responsibilities or other parameters of interest between the various sub-assemblies of the system. And then if it is the case, and often in these smaller systems you don't have to do this, but you can sometimes map then the functions that we just talked about to the specific components in the physical architecture. This is what's known as allocation in systems engineering, and like I said, most of the time it's pretty obvious in a smaller system how these things map. So here's the physical architecture for this particular system, and you can see I've got it color-coded. Blue means it belongs to the project. Red means it actually still belongs to the project, but it's a purchased component, and black means it belongs to our customer. So by putting this up and discussing with the customer, they know now what we are planning not to do, all the stuff in black, and also what we are planning to design, and what we're planning to buy. So in one diagram, we get all that. And we also see a rough hierarchical structure to the system. Next is an interface control document. Here we actually use that physical block diagram to identify our external interfaces, and I'll show you that next. It's also useful when we have complex internal interfaces to put those into the ICD, the interface control document. And similar to our PRS, each interface is defined by a set of parameters. So it has a name, a number, a written description of what the interface is, and then it has a detailed technical description of the electrical, mechanical, and software interfaces. And then we also verify our interfaces and assign ownership, similar to the PRS. Now, a lot of the interfaces will be repetitive with the design. So a good example is our stand and it's mounting to the skid. So it was mounted with 4 bolts in a bolt hole pattern. There's no need in this mechanical interface to redefine that. There's likely a drawing that already exists that has those 4 bolt holes defined. And so what we'll actually do in the mechanical interface is say refer to drawing 1133, and in that you'll see your bolt holes. And so now people on both sides of the interface know that that's the master controlling document for this particular interface. So I kind of like to refer to the ICD as a series of pointers to other information that already exists in the project. So here's what the ICD diagram looks like. I've basically copied the physical block diagram that we've already talked about and just went around the boundary of our system, and every time I cross over a signal or an interface, I've labeled it. And so here you see the hydraulic lines are an interface, the mounting between the hydraulics and the pipeline is an interface. We have our control signal interface, our RS-232 interface, another physical connection here to the skid, and then our power interface. And then also we have some signals at the top here. So again, at a glance, one can see where are all the critical external interfaces, and this can lead to a dialogue of, all right, well, what do we mean when we have a 24-volt signal here? Does current matter? How are we actually going to transmit that? Is that going to be through a shielded cable, armored cable? So you really start a dialogue as to mechanically, electrically, and software-wise, what do each of these interfaces mean? So next are trade studies, and this is where you start to get into a little bit more hardcore system engineering than the basic stuff that we're talking about before. And these are on our larger System Engineering Lite projects. And you do trade studies when the architecture isn't obvious. Now on smaller projects, like we've talked about, the architecture is often dictated. The customer says in their request, hey, I need you to build me a new PCB that fits in this space, and it needs to look like this old PCB, just make it fit. In that case, you're not probably doing a whole lot of architecture studies. But a lot of times the customer doesn't know exactly what they want, and it may be complex enough that there may be multiple solutions that are not obvious. So this is the tool you use to figure out, okay, well, which direction should we go? So our typical process first is, given the constraints that the customer has given us, let's brainstorm different architectures that can support those requirements. And this is usually a multiple-hour meeting with senior people, and we figure out a bunch of ideas. Then we use the criteria typically given to us by the customer, but often we generate it ourselves, to just say, hey, these are the go, no-go criteria, just to weed down the really out there concepts. Because part of our brainstorming is we accept all ideas, and we don't really discuss why any one idea is better than the other. The brainstorming is focused on generating the ideas. Then later, the team will use the go, no-go criteria to weed out the really bizarre ones that may not fit at all. Then you'll have often a rapid feasibility study, and this could be just a week to multiple weeks long, and we try to answer as many of the rough answers about these various system architectures as we can to find out information against the criteria we're actually going to use to make a decision. Then we put a decision matrix together to pick the best candidate architectures, and I'll show you that on the next slide. Once we've got our best architectures, we then do a deeper investigation into the best solutions. So this may be maybe only 2 or 3 solutions, and then we'll use this deeper study to then down select to begin development. So this is what a decision matrix looks like. There's lots of different versions of this. You put the concepts on one axis and your decision criteria on the other axis. You'll often have weighting factors. You have to be careful with these because these can really skew your results. And in this particular example, what we're saying is the high performance and small size are about 3 times more important than short development time and about twice as important as a low cost of goods sold. So depending on how you rank these criteria and how you weight them, you can actually get different results. And so the engineering team will go through and take each of the concepts and grade them on a scale of 1 to 10 against each of the criteria. And this is actually, at this point, still done by a engineering intuition level. You know, with only a multiple week study, you can't really go deep into 15 different concepts. But you use that initial intuition and that initial study to come up with your top 2 or 3 concepts, and then do the deeper dive on those highest ranked concepts. There's a note here to be careful with biases. A strong-willed person can easily skew these results. Also, don't be trapped into thinking that the decision matrix knows all. It's really just going to output whatever you input. And then we also often have the customer, we teach them how to use this, and we have the customer do this evaluation on their own using their engineering staff. And then it's always interesting to see what their top ranked ideas are versus our top ranked ideas. And that usually leads to a dialogue and then a combined top set of ideas that we go and evaluate further. So now we're getting into more complex systems where we have to use some more advanced tools. This one is use cases. And we do use cases when we have lots of different users interacting with a system. And what use cases are is we identify all of these different players. We call them actors in the use cases diagram. And we identify who they are and what they're going to be doing with the system. And that usually then leads to understanding deeper level functionality that's required. And similar to the EFFBD, you want to bring in that same group of people and help them generate what these use cases are. Again, the people you may not think have an input into this will definitely have input for different areas. So again, those installation, repair, and maintenance people definitely have input into how to install a system and how to maintain it, and what their interactions are, and those can easily be lost if they're overlooked. But having said that, not all stakeholder opinions carry the same weight. So you do have to be careful not just to take every crazy idea. You have to filter through these things a bit. The use cases diagram is very simple. You have all your actors on the outside, you have your system, and then you have the dialogue with the customer and with your team. All right, well, what does a client actually want to get out of the system? Well, they do these particular functions. And what does the installer have to do? Well, obviously they have to install it and configure it the first time. And likewise, the maintainer has to configure and maintain the system. Now, each of these ovals that you see now has perhaps multiple use cases within it. And they also have so they each have a story to tell, and that story starts with a precondition. So what has to be set up before we start function B? Then we run through, okay, what does function B actually entail? And then what do we expect the system to look like at the end? So that's the post condition. So you kind of have a before, during, and after dialogue about each of these functions. And like I said, each of these functions can have different sub-use cases underneath it. And then this, on these more complex systems, is then used to build the enhanced functional flow block diagram, which is the details of these use cases. Finally, the user interface document. These are used on projects where we have very heavy direct user interaction with the system and we have to give the user feedback. And this is typically a Word document that we put together, and it's different for every system. So these are just general guidelines. We will always do these for systems that have a graphic user interface. And so with GUIs or GUIs, will often be dictated, hey, I want you to follow this particular industrial design practice. So a customer may have existing products that have a certain look and feel. Or they say, make it look like an iPhone or whatever. So you might have to follow certain practices like that. Often when you have a GUI, you're going to have multiple screens that are shown, and you may have persistent information versus temporary information. You can get into the graphics, the animation, status bars. And what we'll often do here to start simple is just do PowerPoint mockups. Just roughly sort of sketch in PowerPoint what a screen looks like. Customer can review it, make changes, and then we give the programmers something to start with rather than just written requirements. We give them something that looks approximately like what we want. Now, we're not just limited to GUIs here. Ergonomics are also very important. So what kind of buttons or handles or interfaces from mouse to touch interfaces do you have? How do we respond? How do we give feedback to the user? Labeling, setups. One that often is sort of forgotten until they want to sell internationally is languages. So not just different languages, but special character sets. Do you have to support Chinese characters or Japanese characters or Korean characters? That can really mess up a interface that's expected to be written in English initially. Along with that, what kind of messaging do we give to the user and what kind of messaging do we give to a technical person? Often we distinguish between the information that we allow a user to see, which may be basic messages, and then once a super user or a technician gets into the system, they may then see warnings or errors or logs. So defining all of this up front is really a great input for the software team. So those are the tools. We do all this really to build consensus. So every time we put one of these documents out, we get the stakeholders and our design team to align with what the project manager, system engineer is thinking about the project. That's kind of the glue of the project. As we said, these smaller projects are often ill-defined. They're started before all the requirements or architectures are known. So this process very quickly helps fill in the blanks and identify what you know and, more importantly, what you don't know. We force this consensus early on. You want to do this in the early phases of the project. There's been many studies that show in personal experience that design changes are easy to implement when the design is still on paper or in the computer. And once you start cutting parts, things get very expensive to change. And what we also do is have our stakeholders sign off on the key requirements and architecture documents. When they make changes, you know they've actually read them. Too often, you'll just get heads nodding and people aren't actually paying attention to your requirements. But if they have to sign it off, that's sort of the next level of getting them to work with you. Finally, this is not a panacea. This is not going to solve all your problems. The project will still change. There's going to be unexpected changes. But what SE Lite's going to do by documenting the system in this manner is going to allow everybody to understand, both within the team and your customer, the impact of your changes or their changes. So you'll, again, have a dialogue about, well, yes, we can incorporate that, but that's going to unravel this other thing that we've already started designing. How do we want to handle that? Is that a change order? Is that part of the scope, or what? So in summary, systems engineering needs to be scaled down for smaller projects. And to put it as a system engineering requirement, You shall not overwhelm small projects with heavy systems engineering processes, tools, and documentation. We use Systems Engineering Lite to bring the systems engineering discipline to the technical project manager in measured doses using tools that they're already familiar with. We use it to increase the communication and understanding both between our internal design team and with our customer. And what we found is that this has reduced project cost. Our customers are much happier with the system, and we feel like the projects are much more successful as a result of implementing this. And that's it for me.
Thanks, James. Now let's move on to questions from our audience. We've already received some great questions, and I thank all of you for submitting those. I encourage you to join the discussion and submit your question at any time via the Q&A function in the GoToWebinar window. Let's get started. Our first question is from Dan, and he asks, are there projects or industries that SE Lite may not be appropriate for?
Yeah, so what I think there is, if you are working in product development and your project could be considered a system, then Systems Engineering Lite should apply. As I talked about, Systems Engineering Lite was designed for small and medium-sized projects. So obviously, if you have a very large, complex project, you should be using systems engineers in a full-blown process, and a MBSE tool I'd even recommend. But we don't use System Engineering Lite on things that we don't consider projects. So for example, we do stuff like research or engineering consulting or staffing engagements where we actually put some of our engineers on site with a customer. So in those cases, typically the customer's in charge of the system engineering, and we're in more of a support role. But either way, whenever we do a project, we define in our project plan right up front what we are or are not going to be doing from a System Engineering Lite perspective.
Okay, our next question is from Marty, and he said that you used the term PCB, and he asked, what does that mean?
Oh, sorry, that was a printed circuit board. So
okay.
I think the example was, a small project, with a single engineering discipline might just be, hey, we need you to update the design of a printed circuit board because some parts went obsolete. So that would be an example of a small project in a single discipline.
Great, thank you. Our next question is from Brent, and he asks, how would you go about ramping up SE Lite in an organization?
Yeah, that's a great question. So this whole talk is answering that question for Synchronous. When we were first introduced to systems engineering, it was hard to figure out what worked and what didn't work, especially on our smaller projects. This is a discipline that is used to design fighter jets and space vehicles, right? So how do I adopt that to my 4-week-long project? But in general, first off, like any new initiative, you need to have executive support to implement this. If you don't have that, you don't have buy-in from the above, it's just not going to happen. And then you also need to have an experienced systems engineer or engineers on board to help define what these processes are. So I've given many examples here, but this is just kind of scratching the surface. So experienced systems engineers can help adopt, how do you write requirements and set up a PRS, for example.
Okay.
And then, instead of trying to just steamroller and say, hey, everybody has to do Systems Engineering Lite on every single project, what we actually did was we started creating this methodology, and then we used a couple of pilot projects like the one you saw to see what worked and what didn't work, and we refined our processes and then rolled it out to the broader community.
Okay, our next question, I'm actually going to combine two questions, one from Matthew and one from Donald, because they were talking about tools. One specifically asked, what parts of this do you do in core, but the other asked, what tools are you using for this? So we'll combine those together and ask, what your team does in terms of tools.
Sure. So we do use core for our larger projects. So the project I'm currently working on right now is a multiple $1 million project, and I'm the systems engineer on it, and I use Core for all of my requirements and a lot of my verification activities as well. I still use kind of a more enhanced version of the System Engineering Lite architecture um, tools for that project. But we actually use SharePoint, Microsoft SharePoint, I believe, to manage our projects. And so a lot of this stuff can either be done directly in SharePoint, like the PRS can be a list in SharePoint, um, and the documents we maintain in SharePoint libraries. You can also do a PRS. That's the most critical one, and that's what I'm talking about a lot. Prior to SharePoint, we used Excel to manage our PRSs. And then, like I said, Word or Visio, these are great tools for putting documents together. PowerPoint and Visio are great for putting those flowcharts together and those architectures. So they're all fairly common tools. I would not recommend somebody just starting out using Core on a small system engineering light project because they'll just get overwhelmed. So.
Okay, so you would recommend if it was a bigger project or one that was more in depth, that's when they would get into a more advanced or complex tool.
Definitely, yeah.
Okay.
Well, and I would say, and people have done these types of large projects, and that's what they did in the past. But now that we have these tools, the tools are far superior to trying to do it in Word. You know, like Core, for example, all the traceability is built in. So without a tool to set up like a database like that, you're doing that traceability fairly manually, and it's kind of a pain.
Mm-hmm.
So that's why Systems Engineering Lite, you can only use up to a certain size before just trying to manage all that and track all that becomes a little bit overbearing.
Right. Well, that's a great segue into a question from Keith because he was asking about traceability. And Keith says that this assumes that you have a one-to-one mapping of requirements to test cases. Do you have a traceability matrix example that you use, or do you simply use multi-columned product requirement specifications?
Yeah, so again, these requirements tend to be simpler. I think for the example that you saw, that project we had 40 or 50 requirements total. The majority of those could be tested via inspection or demonstration. Um, but we did have a few tests. We had some environmental tests. We had to put this in a very cold environment and very hot environment. You can imagine these pipelines see snow in mountainous environments, and in deserts they see 120 degrees Fahrenheit. So we had to actually test it in both of those extremes. So in those cases, we took it to a testing lab and put it in a thermal chamber and put it at both of those extremes. And so for that, we didn't try to shoehorn our results and everything into a SharePoint list, but rather we said the verification for the environmental specifications was see this document, and there's a document number, and that document number had the procedures and the results and the discussion about that testing in there. So you can have like a one-to-many relationship. One requirement may lead to multiple tests, and you still have that traceability because your PRS says see this document, and that document in our case is in SharePoint. Everybody can find it, and yeah, don't be afraid to use multiple documents to accomplish these tasks.
Okay, great, thanks. Our next question is from Becca, and she asks, how much time should be spent on SE Lite for a given project?
Yeah, yeah, that's a really good question too. We've sort of figured out for these smaller projects that the PMSE role combined works well. And on a smaller project, you might have a part-time PMSE, and that project manager may actually be managing multiple projects. So their actual systems engineering time, is actually a fraction of a given project. I don't have direct numbers for you, but I know that Eric Honor and the Nkosi handbook both talk about this, and they say around 15% of a project ought to be systems engineering, and they have some numbers to back that up. And what they found is any less than that and the system complexities tend to get out of hand, and any more than that and your documentation can threaten to overrun your project. So I'd say something like that applies for System Engineering Lite as well.
Okay, and that leads to another question from Ashley where she asked, won't this make a project more expensive?
Yes, it will. But in the same way that project management makes a project more expensive, if projects could run themselves and everybody could instantaneously and unambiguously communicate everything to each other about the system, yes, then we can certainly get rid of our overhead of project management and systems engineering. In the last talk, David Long said that, and I thought this was a great quote, that every project has a certain amount of systems engineering that will get done. The only question is when. So even these smaller projects that don't have someone with the title of systems engineer, they're still doing systems engineering. Someone is doing it somewhere, and often it's just in the project manager's head or a technical lead's head.
Hmm.
System Engineering Lite just brings that a little formality to it, and then encourages the communication and collaboration with the rest of the team and with the customer, rather than it just being kind of locked up in somebody's head. So this will always bring potential issues to the forefront earlier, we found, than later. So from that perspective, no, it's not going to cost more. It'll probably cost less because you identified the problems when they were less expensive to fix.
Okay, that leads me to a question I'm sorry, I'm so tongue-tied today. The question is from Mohammed Riza, and the question is how system engineering can help the project manager to shorten the product lifecycle.
Yeah, so like I was just talking about there, by identifying your requirements up front, your architecture up front, interfaces up front, your verifications up front, um, then you establish with your customer what is this project really all about, because again, these small projects tend to be ill-defined. They get started before you have answers to everything, and by answering those questions earlier, um, you'll make the project cheaper and faster.
Great. The next question is from Andrew, and he asks, in trade studies, when comparing more qualitative criteria, is there a tool or a way to conduct pairwise comparisons?
Yeah, so if you in that decision matrix that I showed, that show a number of concepts, and we will often generate 10, 15, 20 concepts for that early decision matrix. Once you and the customer go through the sort of high level engineering intuition level of filling that out, you'll typically have two or three concepts that filter to the very top, and I think that's what he's referring to, that pairwise comparison. What we do after that is then a much deeper trade study, and that will typically be documented in Word, as a written document, and then in a presentation format. And there we do a deep dive into the costs of a particular system, pros and cons, technical attributes, and depending on how much time the customer wants to get in, our trade studies are often 6 to 8 weeks to really answer very in-depth wise the pros and cons of a couple of different systems. And that way you feel like you have the best information at that time to decide what to actually spend the money on going into development.
Great. Our next question is I'm combining from a couple of folks, Matthew, Richard, and also from Kent. And they're asking about an overview, almost a flow chart of the SE Lite process. And further, do you have a graphic representation of SE Lite that shows what the question says is SE heavy that would fall outside of the SE Lite process?
Sure, so let me go back here. So I don't have a direct SE Lite representation. This slide here outlines all of the tools and kind of gives you a rough guideline that you always do a PRS. Most of the projects can probably benefit from a physical block diagram and the functional flow. And then the more complex ones get into these other tools. Our process for system engineering, this is kind of a snapshot of the system engineering activities of a larger product development process that we have. And projects typically start for us in phase 1 with requirements gathering and analysis. This is where we start putting the PRS together. We often blend phase 1 and phase 2, so the requirements then lead to discussions about the architecture. This is where we might get into our trade studies, and actually we might combine that with a little bit of rough CAD modeling if it's a mechanical project. So this kind of gives you an outline of the overall system engineering process. Once you get out of system architecture, though, you're in hardcore development. So now you bring on a full engineering team. You are running with the design that everybody agreed to in phase 1 and phase 2. But these two phases set the tone for everything that follows. And then after phase 3, we have our verification activities. And then once those are verified, you move into design transfer. And for us, typically we hand over the project because we're doing contract engineering sometime between 4 and 5. Often our customers want to do the verification, or we will do initial verification and then they'll finalize it.
Okay.
I don't know if that answered everything you asked.
I think it does. I think it does. And if there's any lack of clarity for anyone or a follow-on question, they can always post it on the forum at our community site, and we'd be happy to engage a conversation there where we can have a little bit more two-way flow. Just a few more questions, if you're okay, James.
Yeah.
The next question is from IPEC, and the question is, do you follow up on organizations you've worked with who've used your SE Lite on your projects, and do they keep using it as they go into other projects?
I have not followed up directly. I do know anecdotally that we have a better dialogue when we use System Engineering Lite. There's a lot of project managers at Synchronous, and the ones that have been using it are really happy with it. One interesting thing that happened is we have one customer that we've gone back, they've actually come back to us on multiple projects, and after I did some System Engineering Lite on one of our projects, this is just a small $100,000 project for us. So I used these tools, and then the very next project that they proposed to us, they sent us a request for proposal, but inside that RFP, they had these tools listed out. Now, there's no way they knew those before they had this project prior. So I know that it resonated with this particular customer because they came back and actually requested those same tools to be used on the new project. So I think it's making a difference.
Absolutely. Next question is from John, and he asks about using this Lite process within an Agile project. Have you done that, and what is that like?
I think it can be used in an Agile project, and I'm actually thinking about writing a paper for the next year's INCOSE meeting that sort of tries to combine those together. This here is a waterfall type process that you're looking at on the screen right now, and we try to define the majority of the requirements and the architecture up front. But I acknowledge that requirements often trickle in throughout the project, and I think that can be rolled into your sprints as part of the Agile process, incorporating those. But what you have to be careful about, and this is what I think the gist of my talk next year, if I do it, is going to be, is you have to know what level the changes will affect. So once you nail down what your high-level system architecture is in phase 2, you can't change the high-level architecture once you start developing it. That's very rare and very costly to do. If you start messing with low-level requirements, if nobody's implemented them yet, then yeah, you can roll them in. So the requirements kind of upkeep happens often on these smaller projects throughout development. So I think it is compatible. I have not used it directly on an Agile project, but I think it is compatible.
Well, James, it sounds like you've committed yourself to a paper, so I look forward to reading that.
I know, now it's public.
Okay, and our last question today, this is from Raj, and he asks, when you have different documents and tools, what efforts do you take to maintain coherency and consistency?
Yeah, that's good. So again, we have this combined role of the PMSE, and when I've been in that role, that's my job, is to manage the project both from a project standpoint and from a technical standpoint. And I didn't really emphasize that in this talk, but it works much better to have a technical project manager become the PMSE. We tried it. It didn't work out as well with non-technical project managers. So you have to have a bit of a technical background to really do this PMSE work. And that's your job. That's you are the kind of the glue that holds the project together. And so that person is in charge of, writing the PRS, putting the architecture together, and writing the interface control documents. And so there's going to be a commonality there. And we also have templates that we've developed, so people aren't writing these things from scratch. They have examples to pull from. And so that's all sort of helps to have a common look and feel to all this.
Great. Well, James, that wraps up the Q&A. Thank you so much. I know we had quite a few questions, and a few that might have been a bit challenging, so thank you so much for sticking with us. For everyone else, thank you. If we weren't able to answer your question during the Q&A portion of the presentation today, we will contact you after the webinar to ensure that your question gets answered. If you have other questions or comments that you didn't send in to me today, I do invite you to post those on the forum at our community site. You'll find that at community.viteccorp.com. A recording of today's webinar will be posted to our website, viteccorp.com, by the close of business tomorrow. In closing, I'd like to thank our presenter today. I'd especially like to thank all of you for joining us. And as we bring this webinar to a close, a survey will open on your screen, either in a new browser tab or in a new window. Please take a moment to provide us with feedback on today's presentation and let us know what topics you'd like to see covered in future webinars. Thank you for joining us, and have a great day.